In the morning session, second talk in the morning session, I think Suvrat doesn't need any introduction. So he's going to tell us about infalling observers and information paradox in AdS CFT.
Okay, so thank you very much. So I'm going to, this is based on work, I should say, with Kyriakos Papadimos. And we wrote a paper on this, and we have a paper coming out shortly. So the paper we wrote is 1211-6767, and we should hopefully have one out shortly. So let me just start by giving you an overview of what I'm going to talk about. I want to, yesterday there was a lot of discussion of a summary of a lot of these AMPS problems, and a lot of this is based on at least a tacit assumption that there's a mapping between bulk and boundary degrees of freedom. So before I go on to that, I just want to review that very briefly. As Sandeep was saying, there are these tacit assumptions that may not be familiar to people who work in AdS CFT but have not considered this particular set of problems. So I want to review this bulk to boundary mapping that we examined in this paper, but on which a lot of work has also been done previously. And then I want to say that all this issue that we've been discussing, over yesterday and not today morning, but the issue of the information paradox that we were discussing yesterday and its relation to AdS CFT basically has to do with the existence of certain kinds of operators in the CFT that can describe the interior of the black hole. So these are these operators that yesterday by Gautam were being called B tilde modes, and I'll call them O tilde modes because O are the operators in the CFT. So I want to describe, after talking about this bulk to boundary mapping, why you need to find certain additional operators in the CFT that give you a description of the degrees of freedom behind the black hole horizon. So I want to tell you that in some sense, all these debates are really debates about whether or not these kinds of operators exist in the CFT or not. So I want to phrase the problem of the information paradox in terms of these kinds of operators. Then I want to give you a construction of these operators. So I'm going to try and describe an explicit construction of these operators, which is work in progress, and I'll be very glad to have feedback on this. But I'm going to try and give you an explicit construction of these operators. And after this, I want to then resolve all the AMPS arguments. So let me just remind you, I think we have a good answer to all of the AMPS arguments. Let me remind you there were several arguments. There was an argument from strong subadditivity, which Sandeep discussed in great detail yesterday. And there's a response to that Sandeep discussed, which is, in terms of black hole complementarity, where you have some degrees of freedom outside that mirror the degrees of freedom inside. And, there's a counter argument to that from AMPS, which is that, if you do that naively, it looks like you get a large commutator between the degrees, the early radiation and the degrees of freedom inside. So I want to resolve this argument. There's an argument which I was describing in the discussion yesterday, which is about the lack of a left inverse argument. I'll review these arguments briefly for you if you like again, but we discussed this yesterday. And there's a last argument by Marolf and Polchinski, which I'll call the NA not equal to 0 argument. And after constructing these operators, I want to describe why we have good answers to all of these arguments, and why none of these arguments continue to hold. Okay, so this is the overview of what I'm going to talk about. Before I do that, before I go on to this more interesting stuff, as I said, let me just try and review this bulk to boundary mapping. So I'm going to work for simplicity whenever you want to think of something very concrete in the Poincare patch, so that my metric is I could do all of this construction in global AdS as well, but just for simplicity, we'll work in the Poincare patch, so we can talk about momentum. We can just as well talk about spherical harmonics, but this makes things simpler. And I'm going to consider an AdS CFT correspondence, but the CFT is at strong coupling. Okay? The CFT is at strong coupling. I'll always be at large N. I'm always going to work in a 1 over N expansion. So we have a CFT at strong coupling in large N. And we know the good degrees of freedom to describe the CFT in this kind of a setup are good gauge invariant operators. For example, in the n equal to 4 Yang-Mills theory, you have operators like trace of f squared, or you have the stress tensor. And you have operators of this kind that are good probes of the state of the CFT when it's in this kind of setup, when you're at large lambda at large n. These operators have duals in the bulk. There's a natural physical interpretation of all of these operators. This trace of f squared is dual to some kind of a marginal scalar in the bulk. This T mu nu is what is dual to a graviton in the bulk. And you can write down other kinds of operators in the CFT, and they have a natural physical interpretation in terms of particles that are propagating in the bulk. Okay? So this is something that's well known. But I think what's also well understood, at least within a certain subcommunity and probably not entirely appreciated outside, is that it's also possible to use this mapping of the fact that T mu nu maps onto a bulk graviton to give you a description of local bulk experiments conducted in the bulk of AdS in terms of boundary correlation functions. So in particular, it's possible to take this CFT operator. So by the way, these operators I'll all call O operators. Okay? I don't care about whether you're talking about trace of f squared or T mu nu and what I'm going to talk about. I won't, in general, talk about indices, talk about things with Lorentz indices, but you could very easily add them on. And usually, it's fairly well understood that you can take these O operators and do a Fourier transform, and then yes.
This whole other class of operators.
Yes.
Objects, in the boundary theory.
You mean double trace operators?
No, a trace of, f square, something.
Okay. So as long as...
So let me finish. And if the string of operators has to be very large, if you want to, for example, account for black hole entropy, actually.
I'm not talking about black hole entropy at this level.
Yeah, but
I'm talking about light operators.
Black holes, no, in this
yes,
talk.
We'll talk about black holes, but I'm not going to talk about black hole entropy in this sense. I'm not going to try and count black hole entropy in terms of...
No, I'm just saying that it might be important to consider there are Wilson lines, there are Wilson loops,
yes,
there are all these long operators, strings of operators.
There are many kinds of operators, I agree, but I think from a perspective of giving a description of semi-classical physics in the bulk, you generally don't need these operators. In terms of effective field theory in the bulk, you can talk in terms of gravitons and maybe string excitations, which you can try and add on here. But you generally don't need to consider extremely complicated operators, and I'm talking in terms of effective field theory in the bulk. So I'll talk about graviton excitations or scalar excitations.
But and I thought you were talking about black holes at some point.
But you're not trying to create black holes out of
all the discussion we've been having so far is in terms of operators.
So you're staying outside the black hole.
No, I'll talk about inside the black hole also. Inside the black hole also you do.
I understand that I'm getting to a certain point. Which
I see. I agree with you, but as we have discussed many times, it's not clear. It's not clear at this point that the detailed description of the black hole in terms of microscopic degrees of freedom is relevant for these kinds of questions that I'm going to ask about, unless you go very close to the singularity, as we've discussed many times. So you can raise the question again if you like when we come to this.
All right.
As far as I see, I don't think that understanding very complicated operators in the CFT is very important for understanding effective field theory in the bulk. Maybe it is, but so far it's not clear that it is.
So your region is just a supergravity or gravity, not a string.
No, you can do string theory. You can if you like you can add on also stringy degrees of freedom.
But in this talk you consider only light degrees of freedom, is that right?
I just haven't written the stringy degrees of freedom, but you can think of operators that are dual to stringy degrees of freedom as long as they're lighter than n. I just, lambda is large, but n is much larger than lambda. So I'm always at weak string coupling. I always want to be at weak string coupling, but so there's a hierarchy between the Planck and the string scales, but I can add on stringy corrections in consistent way. Okay, so let me just try and summarize this formula that I wrote on the board. So you take one of these operators O, you do a Fourier transform along the boundary directions. Let me remind you this operator only lives in the boundary dimensions. I've picked out omega because I'll always be working in a Lorentzian version of the AdS CFT correspondence. So I Fourier transform this operator, and then I multiply it by an appropriately chosen mode, and this mode has to be carefully selected. And if I select this mode carefully, then it turns out that you think of... Now, let me remind you that the boundary operator only lives in these boundary degrees of freedom, but I've put a Z here. Okay? So this is still a CFT operator. I've taken one CFT operator, I've Fourier transformed it, and then I've reverse Fourier transformed it, although with a slightly different function. And if you think of these kinds of operators, these kinds of correlation functions, then you can show systematically in a 1 over n expansion, in to be honest, this has been done at leading and next to leading order in 1 over n. These kinds of correlation functions taken in the CFT. So let me be in the vacuum for now. I'll come to an excited state. These kinds of correlation functions of these CFT operators have the same kind of behavior that you would expect of a scalar field with the right dimension to be dual to O. Okay. And that relies on a particular choice of these modes zeta. You might sometimes see this formula written in this form. And in this language, this is called a transfer function. Okay. This function k is called a transfer function. And this is work that was done by Benna, I think Banks and others. A lot of work done by Kabat and others. And I'll describe some new stuff that we added to this. Okay. So this is something that's fairly well understood. And this is how you use, you can use this map to go between, what you want to talk, when you talk about results of experiments in the bulk and results of experiments in the boundary. Okay. And the reason I want to emphasize this is that usually we say, the only kinds of observables are these S matrices. Where you do some asymptotic experiments in the bulk, you send in some particles at infinity, and you get back some particles at infinity. But actually, we can do more. We can actually also ask the results of at least approximately local experiments in the bulk by means of this mapping.
Sorry, as already came up,
yes.
To do this, you need to know what the bulk background is. Because you're solving some wave equation.
No, I think you don't, because I think the point is that this zeta, no. So this zeta omega k, you're right, is the solution of a certain wave equation. But if you chose a solution of a different wave equation, you can't just multiply this with solutions in some other background and expect to get local fields in that particular background. So the fact that this map works is very non-trivial. For example, one of the non-trivial things that enters here is that if you think in the vacuum, as I was saying yesterday, if you think of an endpoint correlation function of this kind, and let me say that, and if one of these guys is space-like, let's say this guy is space-like, then this is down by 1 over n if kn squared is greater than omega n squared. This is already a non-trivial property, and its properties of this kind, especially at 1 over n, they tell you that if you multiply this with the wrong functions, with functions not the AdS modes, but with modes from some other space, you wouldn't get the correct kinds of local fields. So, this is something, you're right, is chosen by solving the wave equation, but it's not like you can solve the wave equation in flat space and expect to reconstruct local fields in flat space by using boundary fields in AdS. So there are strong constraints in this map.
That I agree. I'm just saying, when we are saying that you can have a description of local physics in the bulk from the boundary, because we have a map like this, how much more than the following are we saying that we already know the bulk and we are interested in small fluctuations about it, and since we already know the bulk, the data on the boundary, once specified, tells us everything about the bulk. This is a slightly more sophisticated way of, for coherent states, it's exactly that statement.
It's a slightly more sophisticated way of that, I agree, except that there's a consistency condition in this.
Okay,
for example, this is a consistency. You could ask, how do we know, even to leading order, that you get the AdS geometry and not some other geometry? That's a question you could legitimately ask. That is,
suppose there was a map like that, how do you know
How do you know that this is the solution of the wave equation in AdS? How do you know it's not the solution of wave equation in flat space? And I think the point is, if you try to write down a solution of a wave equation in flat space, this just wouldn't have the right properties to be a local field in flat space. So, by demanding consistency of the map and by demanding locality of the map, especially once you go to subleading orders in 1 by n, it's possible to, basically pin the map down. Or at least the belief is that it's possible to pin the map down. And I can try and give you various arguments about why that's the case. And so, this gives you, the claim is that, there's a unique map, the claim is a unique map from boundary fields to local bulk fields.
That left-hand side,
yeah.
The left-hand side doesn't have any z in it, right?
The left-hand side, this has.
Phi CFT TXZ.
Yes, because I put in a z by hand. I multiplied with appropriate functions. I Fourier transform this and I multiply it with a z.
O is an operator in the bulk?
Yes.
Is that right?
Yes. No, O is the operator in the boundary.
Oh, in the boundary. Oh, sorry.
Omega gain.
I'm just confused by a notation. You say phi CFT. Okay.
It's a CFT operator. This is still an operator acting in the CFT Hilbert space.
I see. I was just confused with the notation.
This is still a CFT operator.
Suppose that these functions that you're multiplying, they solve wave equations
not exactly in AdS, but asymptotically AdS, so that the geometry starts, changing, let's say, towards AdS to cross R2 or some such thing, then would you still have
I don't think it would work in the vacuum of AdS. You might have some state of the CFT in which you could do this, but if you just took the vacuum of the CFT and you tried to consider, see, this is a CFT operator, you can evaluate this in the vacuum, so I'm evaluating this in the vacuum. This operator would not have the right properties to be a local operator in the kind of geometry you're speaking of.
Okay, so I use the appropriate excited state.
Then it might. And as I'll describe soon, in the black hole case, there's a different integral transform that gives you the right answer.
I would think that it should, but if it doesn't.
Probably, yeah. So if you can find the right excited state of the CFT that you know is dual to a particular geometry, then this probably does work.
For coherent states, I think more or less is a statement of solving just classical equations.
It's a statement of solving classical equations. There was a lot of discussion yesterday about going back and forth between the bulk and the boundary. So I want to clarify. In fact, you raised this several times. So how you can go back and forth between the bulk and the boundary? This is how you can go back and forth between the bulk and. If you think this is, if you're willing to accept this, I'm
no, but for inside the horizon. You haven't put in a horizon yet.
I'll put in a horizon in a minute. I'm going to say I want to demand a similar construction behind the horizon, as I'll do soon. And I think that basically you want a construction like this to work in the vacuum outside the horizon and behind the horizon.
Sorry.
And if a construction like this works, then I'm going to say that effective field theory is valid in the bulk.
So suppose I have an operator O, which I know the dual of the operator in the bulk is some scalar field set. So that phi CFT, Z, is it the same scalar field that I know in the?
This phi CFT is a CFT operator. Yes, it does behave like the correlators of the scalar field that's dual in the bulk to this. Yes. Okay, I'm going to stop questions on this point because I have to go on with this.
Okay, sorry. Suppose there is a gap system. In that case,
this is a gapless system. Yes, there's no gap here.
Can you discuss the gap?
I'm on flat space, so there's no gap in the boundary. These modes go all the way down to 0. Why are we worried about that?
I mean, because suppose you want to discuss the operator in IR. Okay, IR CFT, okay, from UV. Then how do you construct this?
Sorry, I didn't understand.
Okay. Suppose there is a, UV CFT flow to IR CFT.
You can turn on various kinds of excitations and then do this, but right now can we just consider n equal to 4 super Young-Mills in the vacuum? And then we can do an RG flow. Yes?
You must go on. You must
yes.
What you claim is correct, here's the test.
Yes.
Get me Vassiliev theory starting with free CFT.
You probably can. Okay. In fact, you probably can. You probably can get Vassiliev theory starting with free CFT. It's a hard task, but I think you can actually. I think you can. It's a hard task because you have to make sure that things are consistent in one band. But I think the belief is that it will pass the test. Okay. Let me go on, please. This is. I'm not sure other questions. Some of them seem to suggest it is obvious, and some of them seem to suggest you don't like this. So we need to have a consistent position about whether you like this or not. I think it's true in any case. So, okay, good. Okay. Okay. So let me try and say, as you said, that sorry, this is just generic thing. Okay, so the next statement I want to make is I want to say, well, you can do the same thing outside the black hole background, but these are different modes. Okay, these are different modes, and you can write down the same kind of mapping outside the black hole background. Okay, so that now within the appropriate excited state, as we were discussing, where psi is a state that's close to being thermal, it's a state which has, h and psi is approximately n squared psi, so it's a very energetic state which is close to being a thermal state. So you can think of pure states in the CFT that are close to being a thermal state. If you do the same mapping now in the black hole geometry with a different function, you need a different function in the appropriate excited state, and then you consider these correlators of this new operator. Remember, I replaced the zeta with an f. Then these correlators have the property, have the right properties to be dual to a field now propagating outside the black hole horizon.
This satisfies the equation.
Now this satisfies, now this F satisfies the new equation, it satisfies the wave equation in the black hole background.
But in which coordinate system?
Are you worried about gauge invariance of these operators?
No, I'm worried about whether you solve it in Schwarzschild coordinates or Kruskal coordinates or Penrose coordinates.
So right now I'm always outside the horizon, so all of these coordinates agree outside the horizon. Okay. I haven't talked about anything behind the horizon. Okay. Everything is outside the horizon. So all these coordinates agree in that. You're right, these operators are not indeed, they're not gauge invariant operators if I write them in this way, because you're talking about local operators and you don't have local gauge invariant observables in, in gravity, but you still expect to be able to talk approximately about local experiments. Okay, now this mapping I want to say is slightly more non-trivial. The fact that this works in the black hole background, and in fact some of the early works that I pointed out, I think did this slightly incorrectly. One of the things we pointed out was that this mapping does work. There were in fact some papers and still are some claims that this mapping doesn't work in a black hole background, but I think it does, and it relies on even more non-trivial properties. It relies on properties that say that if you consider this correlation function in this state psi, and now if you have a space-like mode here, if you inserted a space-like mode so that k squared is larger than omega squared, then in fact this guy goes. In general, we don't know the explicit form of thermal correlation functions in the CFT, except in 2 dimensions where you can check this explicitly. But in 4 dimensions, we don't know the explicit form of correlation functions in the CFT. But nevertheless, based on very general properties, just like the KMS condition and the analyticity properties of thermal correlators that we do understand well, you can prove that this kind of correlation function, if you insert a space-like mode, has a fall-off of this kind, has an exponential fall-off of this kind. And this fall-off is actually key to allowing this map to work. If correlators in the CFT didn't have this kind of property, then in fact such a map wouldn't work in the black hole background.
What do you mean by that? That is, the bulk operators would not satisfy what property?
The bulk operators, so for example, if you, let's see, if you tried to, if the boundary operators didn't have this kind of behavior, then I think the bulk operators that you write down would start becoming singular near the horizon. Would start getting various pathologies near the horizon. So the bulk operators would certainly not look like semi-classical effective fields in the horizon. Okay, so that's the statement. Okay. So this is a summary. I wanted to remind you of the bulk boundary mapping. So far I haven't said anything about this. I've talked about vacuum, and I've talked about outside BH.
Sorry, Suvrat,
yes.
Does this mapping tell us something about bulk diffeomorphisms? I think this came up from the boundary
gauge invariance? No.
I mean,
I've chosen a particular coordinate system.
Right, but if you change the coordinates, it will change the corresponding phi CFT operator. If I change,
yes. And it will look like the same thing in a different coordinate system.
Right, but from the boundary theory point of view, why is that?
And this is a redundancy in description from my point of view. I don't think it's a symmetry. It's that you can use different kinds of coordinate systems to describe this. So it's a redundancy in description.
You're introducing a Z, right?
Yes.
By hand.
Yes.
And somehow this change.
I don't have a very good answer.
I mean, the only non-trivial consistency condition presumably is the energy moment of tensor is conserved at the boundary, right? So, I mean, if there is if the energy momentum tensor was not conserved, you wouldn't have gotten a diffeomorphism invariant thing.
Right, and I think one more non-trivial condition, for example, is you should be able to measure the energy at the boundary. So while these operators look like they're local operators, in fact they have to have a non-trivial commutation relation with the stress energy tensor at the boundary. Now, as you know, if I think of phi CFT in some bulk point, and I insert T00 near the boundary, still at the bulk point but near the boundary, and then I do this, and I integrate this commutator across some, we call this bulk 2. Sorry, the notation is so bad. So I'm looking at the commutator of phi and this bulk. This is fixed by the fact that this is creating a quantum of energy. So there's a certain commutator that is fixed by this. So it's non-zero. Even though these are space-like separated, this is non-zero. That's a sign of the fact that this is a non-gauge invariant operator.
Yeah. So I mean, can I just put it in a defined way? That suppose you use a defined AdS in a defined coordinate system. The case will be different, right? And so you will introduce your bulk operators differently.
Yes.
But their correlation functions should be related by diffeomorphism. That should be, one should be able to show this.
Yes.
Using the fact that the energy momentum tensor in the boundary theory is conserved.
Yes, probably.
Right?
Probably.
I mean, nothing else should be needed.
Probably. Yeah. Yeah. Okay. This check has not been done in any detail, but yeah. This check has not been done in detail, but yeah. I have a feeling that, yeah, this kind of check might, in this way of working out, might come out in some automatic way. It might be useful. Yes. Okay, I agree. Okay.
So may I ask one question?
Yes.
So I'm a little confused about the role of boundary operator O in the formula phi. Means that phi O is a boundary operator, and adding means multiplying those f's, you are also constructing another boundary operator phi. But what kind of computations means what's the speciality of O? Means why does it have to come for n is equal to 4 super Young Mills? Because as far as I understand that this n is equal to 4 super Young Mills theory is strongly coupled. So what kind of computations exactly you hope to do from O? Because you can, O is just looks like a placeholder kind of thing. Means
no, O is not a placeholder. First of all, as I said, there are several general properties you can prove these correlation functions. You're right. If you ask right now, given this map, can I say something very new about bulk physics from this? You can't, but it's a map that tells you. It's a translation between bulk and boundary degrees of freedom, which I just wanted to emphasize, since a lot of this information paradox discussion is in terms of a translation between bulk and boundary degrees of freedom.
Right.
So I want to say that local experiments in the bulk can be formulated in terms of those in the boundary. In principle, this does give you information about bulk experiments. You compute these correlation functions, you compute this transfer function self-consistently.
But how can you compute these correlation functions? Means you can.
In principle, it gives you information. You can't compute these correlation functions independently.
So how do you even know that those kind of construction makes sense?
You know that this kind of construction makes sense based on very general properties of correlation functions.
Well, means general properties, any CFT with those symmetries has those general properties. Means why? Means what I'm asking is that how those correlation functions depend on lambda. If you do not know that, then there's no point saying that how the bulk geometry is coming up from.
This I don't agree at all. I don't think we need to know how the correlation functions depend on lambda. It's not at all relevant in this kind of discussion. So, you can conjecture a certain dependence. You don't need to compute that. I don't understand. What's the question actually?
The question is that if you do not know how those correlation functions depends on lambda, then you are talking about very generic properties of n is equal to 4 super Young Mills.
Yes.
Possibly you are only using its symmetries. And that's not...
I think we are not only using the symmetries. We are using some information about dynamics.
Like what? That's what I want to know.
For example, this is something about the dynamics of the theory, which doesn't follow from symmetries.
And that is something you are calculating from Lagrangian, you are claiming?
No, this is something that relies again on general properties of thermal CFT correlators, not something that relies on the specific theory.
That's the point. So I do not expect that for small lambda...
What is the objection to this? I don't understand.
Objection is that AdS CFT only says that at strong lambda, we have a meaningful bulk geometry.
Right.
Your construction is independent of lambda.
No, it's not. Because if you try, as I said, you have to correct this construction in order by order and 1 by n. And if you try and do this correction order by order, by the way, this is not my construction. This is work that goes back a very long time back, so it's not my construction.
Yeah, that doesn't make it more credible.
No.
Okay.
I think it's completely credible. Just one second. Let me just summarize. Sorry. Let me just summarize. I think there's a very straightforward thing, which is that if you look at the OPE coefficients that you get between O and O, which are in principle calculable, you can compute these 3-point functions. Let me complete, please. Okay. When you compute these 3-point coefficients, you can ask what are the kinds of operators that appear on the right-hand side. When you're at large lambda, there's a very limited set of operators that appear on the right-hand side, because these OPEs of O and O with themselves basically close. Okay? So OPEs of supergravity operators with supergravity operators give you other supergravity operators plus multitrace operators of supergravity. If you're at weak lambda, this is not true. So if you're at weak lambda and you're, for example, trying to answer the question of how do you construct the Vasiliev theory, you look at OPEs in the ON model, the free ON model, you will see there are various operators that appear on the right-hand side when you're at weak lambda, which don't appear. These are the operators that would correspond to stringy excitations. So if you try to, for example, do this construction in the weakly coupled n equal to 4 theory, you would end up recovering the string theory in AdS5. And in principle, this is something that can be done, which of course hasn't been done, but in principle you could take n equal to 4, compute the OPs perturbatively, and then try and ask, are you getting string theory in AdS5? And it's an interesting problem which hasn't been done, but which is almost certainly likely to work. In weak coupling, clearly, because if you compute OPs, as I said, you have to correct this. So when you correct this, the corrections depend on what appears in the OPs. When you take an OP of an O and an O, what appears on the right-hand side?
We have no idea whether this construction works in strong coupling.
Well, the construction works at strong coupling. You don't care about what happens to the construction at, The construction works to give you effective field theory below the string scale at strong coupling, which you already know. Because you know what you know, you already have a prediction for the OPEs of these operators with themselves, for the stress tensor with itself. That's something you know. Now, you can say you don't believe AdS CFT, but if you do, then I can compute this OP and I can insert that and I can check the consistency of this condition. You can ask me, how do I get the string theory at strong coupling? And that's a harder problem, which we don't know how to do. Then I think you can get it because I can compute these O's, and so I can do the computation using AdS CFT and reconstruct the bulk. Okay, but I think it works. Okay. Okay, listen, I'm so far just reviewing what I think is very standard stuff, not even my work, just to, set the language for this talk. So I think, there may be, okay, fine. Let me please go on to talk about some new stuff. Okay. So, in any case, as I said, I think it's correct. So let me just repeat that. Okay. Sorry. Let me talk about what happens behind the black hole horizon. Okay. So, what happens behind the black hole horizon? If you wanted to write down a map of this kind behind the black hole horizon, as I said that, what is the kind of question we'd like to ask? The kind of question we'd like to ask is a question of this kind. So, you have some CFT, it starts with some initial state, you inject some matter at some point from the boundary, so there's some matter that goes in here, this is at some point T0, you wait for a time that's much larger than the scrambling time of the black hole, so you wait some time that scales with log n, and then some other observer jumps in, okay, some observer jumps in at T1. Okay, and some observer jumps in at this point, and you want to try and ask what are the kinds of correlation functions, what are the kinds of observables that this operator measures. Okay. Now there's a well-defined semi-classical expectation for what this guy measures, and the semi-classical expectation is derived by replacing this picture with a picture of the eternal black hole. Okay, this picture is derived by replacing this picture of a collapsing geometry with the picture of an eternal black hole. And then the expectation is if you want the horizon to be a smooth place and you want effective field theory to hold and you don't want this matter to affect much of what's happening here, then the expectation is that you can replace this picture of the collapsing geometry with the picture of an eternal black hole. Okay? And then you can ask what is the kind of construction that you have to do about for correlation functions of this kind. You can see that if you try to reconstruct, try to repeat this construction for operators that are behind the horizon, you would need two different kinds of modes. Okay? You would need modes in the eternal black hole, just in the eternal black hole. You would need modes that are left-moving modes that go in from here, which are the O modes. Let me call this region 1. Let me call this region 3. Okay? You need modes that go in from here, and you need modes that are right-moving modes that are the modes that would have come from region 3. Okay? So those are the modes that yesterday were being called O tilde modes. So to do a construction of this kind, if such a construction is to work, then the claim must be that this phi CFT inside, just at leading order in 1 by n, is given by something of this kind. Let me put in some more subscripts here, where this is the analytic continuation of these modes to behind the horizon. But the point I want to make is that you need new kinds of modes. Okay, and if you can find such, these are the kinds of, this is certainly the way you would do the construction in the eternal geometry. And if the collapsing geometry is supposed to be dual or supposed to be similar to the eternal geometry, the point is that in a single CFT, in a single pure state psi of this kind, you should be able to find these O tilde modes. You should be able to find some new modes, O tilde modes. And a lot of this discussion about the information paradox is really about whether these O tilde modes exist or whether these O tilde modes don't exist. Okay? And let me just try and tell you what are the properties you need for these O tilde modes. Let me remind you that yesterday, as Sandeep pointed out, this eternal black hole is supposed to be dual to the following thermofield double state. This eternal black hole has two kinds of CFTs, a CFT on this side and a CFT on this side, and it's dual to this state. Let me call it the thermofield double state to separate it from this pure state in a single CFT. So when I write psi, I'm talking about a single CFT, and when I write psi thermofield double, I'm talking about a state in a double CFT of this kind. And this eternal black hole is supposed to be dual to a particular kind of entangled state of this kind. So what are the properties you need these O tilde modes to obey? So one of the properties you need them to obey is that the correlation, the coefficient of correlation between n omega k and n tilde omega k is 1. And n omega k is defined as O minus omega k into O omega k. Okay? So you take that Fourier transform, you look at the creation operator into the annihilation operator, and R is just the coefficient of correlation. This is just a statement if you measure n and you get some number, you measure n tilde, you get the same number. So the coefficient of correlation, these two are perfectly correlated.
Because the state is.
That's right, because the state is entangled. So you measure n here, you get some number, you measure n tilde here, you get the same number. So this is the property that you wanted to obey. There's another very important property that you wanted to obey, which is that O tilde omega k into any other frequency is equal to 0. Okay, it should commute with the original operators, as indeed it does in the thermofield double case, because these are operators that are acting on one entire Hilbert space. Okay? So the issue of finding these operators is the issue of constructing the interior of a black hole in the CFT, given this entire bulk to boundary map, is an issue of finding operators of this kind in a single state, in a single CFT. Okay? So this is very important, that the whole issue of the information paradox, a lot of the debates that we've been having are about whether such operators exist in a single CFT. You give me a CFT, okay? The coefficient of correlation, of course, depends on what state you're in. So this is a state. Okay? In the state psi, in a state psi, which is a pure state, and is close to being a thermal state because it has energy n squared, the coefficient of correlation between n and n tilde is 1, and these operators O tilde look like they commute with the original operators. So if you can find such operators, then indeed, using the standard techniques of this bulk to boundary mapping that I described, you can construct the interior of the black hole in region 2. If you can't find such operators, that doesn't mean you can't construct the interior. Maybe there's a more sophisticated solution, using the infalling observer and so on, as we were discussing yesterday. But it certainly makes your task much harder. And if you can find such operators, then you can construct the interior in region 2. Okay? So I want to emphasize that this is what I was saying was about the need for the O tilde. And a lot of the discussion that we were having, a lot of the EMPS discussion is about whether these operators exist or not. Okay,
so,
yeah.
You wanted to construct operator beyond the horizon, right? How does it help to have another copy of CFT?
Because the quantization of fields in this region or in this region is supposed to be similar to the quantization of fields in the eternal black hole. And the quantization of fields in the eternal black hole has two kinds of modes behind the horizon. It has left moving modes and it has right moving modes. So the left moving, and which are entangled with each other in a specific way. The left moving modes you get by analytically continuing the modes from this side into this side, but you need some new degrees of freedom, otherwise you won't get a local field behind the horizon. This is another example of why this map is non-trivial. You can't just, if I give you these operators, just the omega k operators, and ask you to construct a local field here, you can't. There's no formula you can write down that gives you a local field behind the horizon. So
then the right moving mode will not be part of that CFT, or will that be?
Well, so I want to find the right moving modes in a single copy of the CFT, at least in some effective sense. If you can find them, then indeed you can, you can replace this picture with this one. If you can't find them, then you're in trouble. Then it's saying that this geometry is not similar to the eternal black hole geometry. Yes?
Even in the eternal case, as you know very well, if that point is moved sufficiently close to the horizon, but still on the other side, in region 2.
Here or here?
Here. Yeah. Then, if you try to create a mode there, sometimes there is a huge back reaction.
If you try and create a mode here, if you create a mode in the past, then indeed there's a huge back reaction.
Yeah. So what I'm trying to say is, if you repeat this construction for that mode, you would try to solve a wave equation.
No, I want to emphasize I wouldn't. I don't want to solve the wave equation from here to here. I don't want to do that. That's you're right, absolutely. If I try and solve the wave equation from here to here, I run into all sorts of problems, because you could say, oh, what if I threw something here that would spoil the solution of my wave equation? I want to solve the wave equation locally in this region, and this is just a picture for intuition. It tells you that when I solve it locally in this region, I get two kinds of modes just in this region. One are left moving modes and one are right moving modes. So I'm close to the horizon.
I agree with that, but what I'm saying is, if we go to the single CFT, what basically was done in that map was that for boundary conditions on the boundary, you solve the wave equation in the bulk, right? Yeah. Now, what I'm saying is, if you take a general disturbance inside and you try to do that, to translate the problem to boundary conditions on the left and right CFT, and then couch that in terms of operators, generically, even without other stuff falling in, you're going to have big back reaction issues.
I think maybe to phrase your problem in this way, you're right that if I construct a map at this point, or let's say at this point, by throwing it here, and now I create a disturbance.
Here, of course, you will have it with the matter.
No, but here also you can create the problem you're referring in the following way. Let me jump in at T1. This is T1. Now let me actually throw in a disturbance at T1 rather than jumping in at T1. So let me throw an infalling observer, and the infalling observer himself disturbs the geometry a little bit. Now let me jump in at T2, which is T1 plus twice k log n, which is closer to the singularity in this diagram. Then it's true that effectively the O tilde operators that the first infalling observer used are actually not so good for the second infalling observer to use. Because the first infalling observer has indeed created a disturbance for modes here, so that the modes that survive for the later observer are what, for this guy, were ultra-Planckian modes and could have interacted strongly. That's something that actually we'll have to put in the map. So if you could ask me the question later, that's related to this frozen vacuum construction.
That's a nice way to put it.
So you can ask the same question in a single CFT. You have something jumping in, you do an experiment, then you throw some more matter in, you wait scrambling time again, and then you ask again what happens.
I see.
So you can put that.
But in general, you'll encounter high energies, is my point here.
If
you
you'll encounter,
try to repeat the map.
You'll encounter high energies if you try and solve the whole setup from here to here. If you try and describe this whole thing in one experiment, where I first throw in some matter, then I wait, and then I throw in some additional matter, then you're right, I'll have to solve degrees of freedom. Although I think it's a 1 over n expansion. I think it's something that can be done. There's nothing exponential about it. It's something that may still be, if you wait a scrambling time, that gives you a 1 over n factor that you need to take care of. So, you wait, as long as you wait a finite number of scrambling times, it's still a finite order in 1 by n.
Okay, I don't agree with that. I think it's
It's trans-Planckian, but n is Planck scale. So it is trans-Planckian. 1 by n indeed makes you sensitive already to effects that are strong effects. It is. That's right. Because you get a boost from here to here.
Just to make sure, that computation ratio is all omega and k, omega prime, exactly 0, that above.
This?
Yeah, that one.
So I'm going to find later that this is 0 when it's inserted within correlation functions with a finite number of insertions. I'm going to find it's 0 for all effects and purposes. I'll try and explain the rest of the talk.
And O tilde you expect to be unique?
O tilde, okay, so the construction I'm giving you is not going to be enough to uniquely pin down O tilde, but it's true that these non-uniqueness is again something that will not matter within low enough point correlators. You could try and expand the accuracy of this map so that you really pin down O tilde. That's something that we haven't really thought about very carefully. But you could try and make O tilde unique. If you ask for O tildes that behave the correct way in the 1 over n expansion to some finite order in 1 over n, then O tilde is not unique. That's the same answer here actually. You could take this answer and you could add various kinds of terms that would still behave correctly at 1 by n. Now you demand that the map is correct at 1 by n, you fix those terms. Then you demand the map is correct by 1 by n square, you fix the additional ambiguity. So you always have this kind of ambiguity which will happen here at the level of precision at which I'll try and describe this.
So this label omega in O tilde,
yes.
is that omega still
yes, so for simplicity I've set up some tx coordinates behind. There's of course 2 patches you have to make. You set up some txz coordinates here and some txz coordinates here. And you don't, if you like, you can set up Kruskal coordinates, in which case I'll get rid of the omegas. But it's nice to talk in terms of omegas because, these a omegas, the a omega that corresponds to this now is very similar to the a omega outside, except it has the opposite energy, for example. So, it's still nice to talk. These are like the modes that are seen by the Schwarzschild observer here in this region. So it's still nice to talk in terms of these modes. Of course, if you wanted to do it precisely, you could do it in Kruskal modes. These are the Hawking partners, exactly. Okay, so this is something which I hope I've persuaded you about, that you need these O tilde modes to construct this map, and this is another reason why this map is non-trivial, because you can't just, if I just gave you these operators and you said, now let me construct the interior, you can't. You can't construct the interior just from these operators. You really need some new operators in the CFT. Where are those new operators? Okay, so that's the question. Okay, good. So let me try and describe to you the construction of the operators in a toy model, and then I'll describe the CFT. The toy model is very simple. Yes, let me go on and I'll tell you in what sense the commutator vanishes. So, in a single CFT, you could ask, what sense does the commutator have to vanish? Why does let me go on and I'll come back to this question. I think it's the central issue here and what I'll say. Okay. Yes.
So suppose I'm at 0 temperature.
Yes.
I know all the operator in the theory. I know uniquely all the operator here, right? Now I heat up from the AdS point, I now heat up and I get a horizon now. So how am I going to get this extra operator?
How do you, yeah, so I'm going to describe how you get these extra operators. Give me a second. That's the rest of the talk, how you get these extra operators. Okay, let me first give you a toy model, which is very similar to the CFT in some sense. And let me try and describe how you can double operators in a toy model, just in a simple gas. And then we'll come to this. Now, I want to say that this is a rather strong kind of problem, because this is saying that these operators are correlated with these operators. But remember, I can, by constructing a small black hole in this and allowing the small black hole to evaporate, I can in fact end up with a state where the state of the CFT is described almost by a Fock space of gravitons. So I can end up in a state where, when most of the black hole is evaporated, when the state of the CFT is in fact well described by just a Fock space of gravitons. So you have to be able to do this doubling in some sense, even in a system as simple as just a Fock space of gravitons on top of the CFT, which still has some energy n squared, but just a Fock space of gravitons. So I'm going to now try and describe how you can do this doubling in a slightly artificial toy model, and then I'll tell you why the CFT naturally has the features that I'm putting in my hand in this toy model. Yes, so that's the kind of question which I think you have to answer by looking at subleading terms in the 1/n expansion. So, it's actually the question I think is slightly different. For example, you could ask, let's say I'm below the Hawking page transition temperature. Can you construct the O tildes? I think the answer is yes. Then I think the question is whether you can use the O tildes in any sense to describe local experiments. And I think the answer to that is no. You can construct the O tildes also when you're below the Hawking page temperature, but this local field expansion that you write down will never need to use these O tildes. I think that's the answer, that the O tildes will somehow have to appear on the other side of the horizon. This is a question of how, in this kind of setup, you detect the presence of the horizon, which we don't have a good answer to, but we think should be doable by measuring correlators and basically seeing when you get something like the horizon. So, okay. Let me give you a following toy model. Okay. So think of, in fact, the gas of S waves that's emitted by a Hawking. So you have some black hole, it emits in various modes because of gray body factors. Let me think of them mostly in terms of S waves. I want to remind you this is a toy model. And so there's a black hole, it emits, and I can draw a big box around this with a radius that's the page radius. Okay? So it emits in some frequencies, and I can think of a gas of S waves that live, spherical S waves that live between the black hole to the page radius. Okay? So if I quantize things, a scalar field in this, there's a lowest frequency that can appear. That's actually proportional to 1 by m cubed. I'm going to put in some factors by hand. Okay? And this is roughly 1 by r page. So there's a lowest infrared frequency that will appear here. So you have a black hole, it's evaporating, the evaporation has gone up to the page radius. Roughly, it's like doing physics in a box, and this is the infrared lowest kind of frequency that appears here. What are the other kinds of frequencies that appear here? They approximately integral multiples of this frequency. Okay, but I'm going to make a trick to mock up some of the behaviors of the CFT. If you just have S waves, it's like doing quantum field theory in just 1+1 dimensions of a massless field in 1+1 dimensions. And if you just have a decoupled theory in 1+1 dimensions, that actually doesn't have some of the features that I will need essentially. In particular, just a decoupled collection of simple harmonic oscillators or a decoupled collection of S waves has a high degeneracy in its energy levels, which is bad for me, and which doesn't exist in the interacting theory, certainly not in n equal to 4 theory. So I'm going to mock that up by making these frequencies incommensurate. Okay? And I'm going to say that the frequencies that enter this problem are given by p omega IR plus some delta p, okay, where delta p is much, much smaller than omega IR. Okay? So they're approximately integer multiples of this, and there's some delta p. This is obviously a feature I've added by hand just to get some features of the interacting theory in place. Yes.
If I quantize modes in AdS,
yes.
Say global AdS or probably
yes.
with a black hole, I haven't
yes.
thought, you will get quantization of the frequencies.
Yes, you
right?
will get quantization.
So what was your comment that
you get quantization of frequencies, but in the end, when you think of the energy levels that you get at a particular energy, the interactions will break the degeneracy. So if you just have a free theory, they're highly degenerate energy levels, which is bad for me for a reason I'll explain in a minute. In interacting theory, you break the degeneracies in this. So I'm by hand shifting the frequencies from quantized frequencies by a little amount to get non-degenerate energy levels. Okay, this is just a toy model. I'm doing this by hand to mock up this feature of the interacting theory. Okay. So of course, I have an expansion for the field here, which is in spherical waves, which looks like plus hc. And let me forget about the left moving modes, the right moving spherical waves. I'm even putting a root p and an r, but this is not important for me. I'm interested in the dynamics of these AP oscillators. Okay? So there's some quantization of the field you can do here in terms of these kinds of frequencies that appear, and I want to remind you that I've made them non-commensurate in a slightly different way. Okay? Now, just for convenience, I'm also going to define n equal to m by omega I. So this black hole has some mass m, so there's some energy m here. That's the m that appeared here. Okay? So this is the lowest infrared frequency, and there's some energy of order m in this gas of S waves. Okay. So the first question you can ask is, I'm going to take a sharp band of energies. So I'm going to consider an ensemble or collection of these S waves with total energy between m minus delta to m plus delta, where delta is some width. Okay, that's not going to be important. So I'm going to consider some microcanonical ensemble of this gas. Okay? And you can ask, well, what is the number of solutions? What is the entropy of this configuration? And in fact, you can check that this energy is given by sum of np omega p, which is just sum of np into p omega IR into 1 plus delta p by p omega IR, if I got this right. Okay. And now if you ask, when is this energy between, so I want to say m minus delta. I hope I'm being clear here. I'm just setting up a toy model and I'm counting the number of states in this band of energies. Okay. If you set up this delta and small delta correctly, the number of solutions you're counting here is just the number of solutions to the integer equation, which is npp is equal to n, where n is defined here. Okay. As you can see easily, I divide by omega IR on both sides. M by omega IR is n. Okay. And the number of states in this band is the same as the number of solutions to the Diophantine integer equation, which is npp is equal to n. Is everyone happy with this? If I set up delta and this correctly. Okay, so this is just to mock things up a little better. What's the log of the number of solutions? Log of the number of solutions is in fact just given by Cardy's formula for large n, and that's just pi. You can check from the formulas, m Planck squared. Yes.
Some relation between capital delta and little delta.
No, I just want to set it so that being in this band forces you to have this relation. That's all I want to say. Okay. Which is just S, which is in fact just the entropy of the black hole. Now you shouldn't take this very seriously. You shouldn't take this very seriously because I obviously put in some fudge factors here by hand. Okay. But you can roughly arrange for this gas of S waves to have the same entropy as that of the original black hole in a very natural kind of counting, just by saying that the lowest infrared frequency is 1 by the page time. So it's kind of a nice thing. You set the lowest infrared frequency to be 1 by the page time. The total energy is the mass of the black hole. As it is, you count the number of configurations that you get the black hole entropy. Okay? Up to a numerical factor that I inserted by hand to get the right black hole entropy.
There is also that inertia of the spherical harmonics, but that probably doesn't matter.
For the spherical harmonics, yeah, there's also, for spherical harmonics there probably isn't, but for the higher harmonics there is. The L into L plus 1, you mean. Yeah, for the higher harmonics, I took S waves.
Okay.
I was taking S waves only. These are only S waves. They have this expansion.
Spherical harmonics, you get much more entropy than.
Right. So there's this Toft brick wall counting and so on, which and you can ask, and then he has to put a cutoff on the angle of. I think some of that has to do with counting things all the way down to the stretched horizon to out here. If I consider things beyond the potential barrier, which I can, then mostly it's S waves that are emitted. Not so much energy is emitted in the higher harmonics. The discussion you're speaking about, I think, is this Toft model of the brick wall counting, where you try and count the entropy of the gas, the Toft gas, which is close to, behind the potential barrier, close to the horizon, and you try and put a stretched horizon here. I can think of quantizing the field between something that's 10 times the Schwarzschild radius up to a large distance, and I think this problem wouldn't occur. I think this problem occurs more in the Toft case, if you try and go very close to the...
No, I think even if you take from 10 times to Schwarzschild radius to all the way to this R page, yes, right? Then the amount of entropy that will have, see, this is essentially a one-dimensional gas,
yes,
entropy
yes,
count of one-dimensional
yes,
gas,
yes,
right? They will get a multi-dimensional gas and you will get a power of R page.
You will indeed accept that most of the energy is emitted in this is not the right condition to impose, because most of the energy is emitted in S waves. So, the higher harmonics have less energy. Yes, yeah. So, effectively, it is a one-dimensional problem.
A fraction, right? I mean, it's still a finite fraction of the total black hole mass.
I think you can make it the very high harmonics, which is what you need to get the R-paged cube. I think for that you need to get, actually this calculation can be done precisely. In the end, the Hawking gas has some 40% more entropy than the black hole or something as Page calculated. There's some number. And I think that has to do with the fact that very high harmonics don't contribute, because very high harmonics eventually get restricted to being very close to the horizon.
I see.
So, you're right, you have to make this calculation more sophisticated. Yeah. For my purposes, I'm just interested in the gas of decoupled harmonic oscillators, and I've given it some features to mock up the full theory, and I'll talk about the full theory.
So if you put in the gray body factors, the
higher L's are, I think suppressed. Right, exactly. Okay, good. Now, let me try and construct in this model. You can ask me the following question. Oh, let me keep this in place. In this model, you can ask me, well, okay, now you have this model, you have something that looks like it has the entropy of the black hole. Find for me the tilde operators that correspond to these modes, EP and NP. The question. Find me the operators that correspond, double these AP operators for me. Where are the doubles of these AP operators? Okay. Okay. So let me now define some operators that look like they're double of these operators, and these operators are defined in a particular state. So now I'm going to say something which is interesting and maybe incorrect. So I'd be very happy to take questions after what I just say in a minute. So please give me a few minutes to complete what I'm saying, and then we can stop and have a long question session. So I'm going to define the operators as follows. Okay, I'm going to define my operators in this way. Where should I define them? Let me go here. Space. This formula also I want. Let me erase this. Let me define them here. So EP tilde, so this is a state psi. Now I take a particular state in this ensemble. Now I have many such states. I take a particular state, one state. Okay. Psi is equal to e to the minus beta omega p by 2 into AP dagger psi. Okay. This is what I call rule 1. No, I'm taking a particular state and I'm defining my operator EP tilde to satisfy this property. Okay, this is what I'll call rule 1. And then the next rule is that AP dagger and some other thing, pk to A dagger pk plus 1, A dagger pk plus n, psi, is given by basically moving AP to the left. It's given by AP1 to A dagger p plus n into A tilde p psi. Okay, this is what I'll call rule 2. Okay. Okay. Now this is a set of linear equations that I get for this operator A tilde in this state psi. Okay. How many linear equations do I get?
Psi is one of the microstates.
One of the microstates. So I go to a particular microstate.
AP tilde will depend on that.
AP tilde will depend on the microstate. Okay. Now I'm constructing for you AP tilde which depends on the microstate. This is how many equations do I have? This is a set of linear equations. Each of the lines here is a set of linear equations for this operator AP tilde. How many equations do I have? This is just one equation. It tells me the action of AP on psi. How many operators can I get by acting with a finite number of operators on this psi? As long as I keep this n smaller than the large n, okay, smaller than the total number of oscillators that I have, you can check that you will always have solutions to these linear equations. Remember, this AP tilde is living in a space that is of size e to the s to e to the s, right? EP tilde lives in a e to the s times e to the s dim Hilbert space. So it's an e to the s times e to the s dimensional matrix, and so I can give you e to the s, I can give you its action on e to the s linearly independent vectors, right? And as long as I keep the number of insertions of these operators, or the number of insertions of these phi operators much smaller than n, you see you don't produce e to the s vectors here. So this set of linear equations does have a solution. Okay. Where can I run into trouble, and why did I need this condition here? I can run into trouble if this psi is an eigenstate of one of these operators. Okay. If this psi is an eigenstate of one of these operators, or by taking a small number of operators I can annihilate psi by taking a linear combination of a small number of operators, then indeed I would run into trouble. So for example, in the non-interacting theory, where I have a degeneracy of energy levels, it would be true in that theory that you think of this operator AP dagger AP, this operator would minus E minus M, psi would be 0. in the non-interacting theory. In this theory, because I have mocked up this feature of the interacting theory by making the frequencies non-commensurate, there is no operator I can construct short of using an n number of psis, short of inserting n number of these operators that can annihilate the state. You see why I would run into trouble if I had something of this kind, if this psi was ever an eigenstate of any operator. You can see that this rule, which says that, commute a tilde to the left, would not be consistent with this rule. If you like, I can explain this more. Okay, I can explain it more if you like. Yes.
You made the frequencies incommensurate.
Yes.
But if the different modes are not interacting with each other, it's still a free gas, just with a strange spectrum,
yes,
right?
But it's not an eigenstate of any of these operators, NP. The state psi is typically an entangled, it's a linear combination of different kinds of eigenstates of these operators, NP. So in general, this operator will not annihilate the state psi. Because, the total, you can check that this operator will not annihilate the state psi.
Sorry, the property of...
The state psi that you have taken is not an eigenstate of energy.
It's not an eigenstate of, it's a, right.
So it could be an eigenstate of total energy, but not individual.
That's right, exactly.
But in particular, since you were giving an example where it would fail,
yes.
had I taken a microstate
which was an eigenstate, yes, then it would fail. Of the NPs, then it would fail. Indeed, if you took a microstate, that's an atypical state. If you took a microstate, it was an eigenstate of the AP dagger AP of one of the number operators, indeed it would fail.
But you're saying a typical eigenstate of the full energy,
right.
Even though the full energy is summation omega p AP dagger AP. Right?
Right, but this is not, this is not a typical, it's not an eigenstate of the energy. It's some state that's taken as a linear combination of states in this band. So it's not an eigenstate of the energy. Right. Not an eigenstate. In the CFT, I'll allow you to take an eigenstate. Here, I won't. In this case, if I take really an energy eigenstate, I run into a problem that this is annihilated. But because I have this gap, this delta gap, I'm going to not allow you to take an eigenstate. In the CFT, I will allow you to have this eigenstate thermalization hypothesis.
And then
this will come about naturally.
Typical state in that band, this will not be true, and you can solve your...
I can solve my linear equations. That's right. How many equations do I have here? Well, I have, roughly n to the n equations. This gives me n to the n equations, which is much smaller than e to the s.
Each of those is n equations. Clearly.
Each of these is one, yeah, if you give me, it's a question of how many operators I can construct by putting n insertions. Roughly each of these I can take to be any of the n's. This p can run from 1 to n. So roughly I can construct n to the n equations, roughly, which is much smaller than e to the s, provided n is much smaller than n. So I can solve these linear equations with this important provision that I'm not in an energy eigenstate. Okay? And that's the reason you see I had to mock things up and remove the degeneracies. Okay, so these are my rules for this.
Sorry, yes, small n is fixed for you, or it can be any?
I'm going to define my operator AP tilde, and you tell me in how high point a correlator do you want it to behave correctly. Do you want it to have these properties? So if you tell me you want it to have the right properties in a 100-point correlator, I'll take n equal to 100 or n equal to 200. But you can't demand that it has the right properties inside a capital N-point correlator. Then it doesn't have the right properties. Well, let's come to a physical interpretation in a second. I think let's discuss this at the end, if you like. For now, I'm constructing these operators. Okay, good. Now, if you like, I can tell you. Okay, do you want me to show you why this leads to an inconsistency? As I said, if the operator psi is in, if by A I call any combination of this kind, I'll call A. Okay, so this kind of operator I'm going to call A from now on, some arbitrary combination. If you ever have A psi is equal to A psi, then clearly you'll run into trouble, right, with these two rules. Because on the one hand, I'm saying AP tilde A psi is equal to AP tilde psi from rule 2, right? On the other hand, I'm saying, from A psi is an eigenstate. So this is the statement that AP tilde, let me call this eigenvalue kappa, sorry, to avoid confusion. K AP tilde psi. So this I can also evaluate as K AP tilde psi, and these two things may not be the same. So if you have an eigenstate of some operator of this kind, then you will be in trouble. Okay? But in fact, you don't have that's the typical property of a thermal system, is that it's not in an eigenstate of any such operator that you construct out of a small number of observables. So this is a key property that I put in, which is a property of thermality, which is that it's not, by acting with a small number of observables of coarse-grained operators, you can't annihilate the state. Okay, so it's very important that the state is not in an eigenstate. And that's something I put in by hand here, which is true automatically in the full CFT.
Suvrat, are you saying that although this looks like a linear system,
yes,
a linear system of equations, but these AP tildes are going to be some nonlinear functionals of psi. Is that right? Because otherwise you could choose any basis of the microcanonical
ensemble.
Yes,
there will be nonlinear functionals for this, absolutely. Because the reason is that you can't make these equations consistent for a, you can't take a full basis. Remember, I'm restricting you to n smaller than n.
Right.
So this is not a full basis for this ensemble. It's a particular state and excitations about that particular state.
I see. That is why it depends on the choice of the basis.
That's why it depends on the choice of the state psi. Exactly. That's why it depends on the choice of the state psi. Okay. I can try and explain to you why these factors e to the minus beta omega p come about. Yes.
Rule 2, I'm not sure what the indices are doing. On the left-hand side...
Rule 2 just says you commute the AP. Whenever you have AP tilde acting on A, you just commute AP tilde so it acts on the right.
So AP tilde in effect commutes with all products
of APs.
Of A and A daggers,
yes.
in any order.
Yes.
So basically they are all commuting with each other.
AP tilde is commuting with each other. AP tilde commutes with A's, with all the A's.
Not commutation with the standard way in which creation and annihilation. You literally...
AP tilde is just separate. It just commutes with the A's. A's and A dagger, it's like the other side. So it just commutes.
Sorry.
So this is demanding that it commutes. Okay? And these kinds of linear equations have a solution.
It commutes only acting on the state side.
Only acting on the state side. That's right. Acting within correlation functions of a finite number of operators. Okay. I can try and explain why I inserted this factor e to the minus omega p, e to the minus beta omega p. The reason I inserted this factor, sorry, I'm running out of space now completely. Okay. So the reason I inserted this e to the minus beta omega p is that if you wanted to really mock up this thermofield double state that I wrote some time back, let me just see. That's right, it has this factor. So remember, what is the state I'd like to mock up? The state I'd like to mock up. The state psi is in one of this band. The real state I'd like to mock up is a state that looks like np omega p into beta. By the way, there's a temperature beta you can associate with the state psi by measuring these correlators of A's and A tildes into sums over all possible kinds of NPs, sum over any set of occupation numbers. This curly brackets means a set of NPs. I hope the notation is clear. Okay, so this is the thermofield double state you'd like to mock up. You can check that on a state like this kind, if you act with AP tilde on psi TFT, what you get is this guy. Let me now act on, it gives me sum of e to the minus beta np omega p, okay? And it removes some operator from here. Let me call this nm to notation here. Okay? It gives me root of np into nm into nm minus delta mp. Now you change the order of sums. This is a sum over nm. Okay? You change it to an nm prime, where nm prime is nm minus delta mp. It's just sum of nm prime. Okay? E to the minus beta omega p by 2. Okay? Beta sum of n p prime omega p prime. Okay?
For the thermofield level, a set of integers nm tilde should be the same as
It is the same. It's the same.
Okay,
I'm just writing them separately because here I'm changing one but not changing the other. By acting with AP tilde, I spoiled the correlation a little bit. I'm just writing them to show that by acting with AP tilde, I killed the P mode here. I reduced the occupation by 1 here.
Sure.
So that's why I'm writing them separately. Now I'm going to change variables to some different sum. And this looks like nm prime plus delta mp into nm prime, which is indeed e to the minus beta omega p by 2 into a dagger p. So a tilde p maps to a dagger p on side TFT. Okay? So this behavior is written so as to mock up the correct action of these operators in the thermofield double state. That's why this e to the minus beta omega p factor appears. If you do the same thing for the spin chain, you won't find this behavior. Okay? Okay, good. As Sandeep already pointed out, these AP tildes, they commute very nicely with these A daggers. For example, let me think of AP tilde with AM on psi. If you like, I can insert one of these operators A, but I won't insert it to lighten the notation, is equal to AP tilde into AM on psi minus AM into AP tilde on psi. But by this rule 2, this is equal to just, I commute this through. This is equal to AM AP tilde psi AM into AP tilde psi, which is equal to 0. Okay. What about this property that I want? Is this property set?
Sorry, Suvrat,
yes.
but you said this, but this cannot be true for arbitrarily large P, right? I mean,
it's true for arbitrarily large P. It's just not true for arbitrarily large, for P between 1 to n. The number of oscillators I have is between 1 to n. It's true for arbitrarily large P. It's not true. If I insert an operator A here, this statement is still true. This statement is still true as long as A doesn't contain more than n insertions. This is true within the state psi on which I define these operators AP tilde, and on any descendant of the state psi produced by acting with a number of ordinary creation annihilation operators that doesn't scale with n, doesn't scale with capital N. So it's true within what I'd like to call low point correlation functions.
And how many are the total? Sorry, you have a band and you have some total number of states.
E to the n.
Is E to the n here?
I have E to the n states. So the number of states I get here is n to the n, capital N to the small n. Number of states I really have is E to the capital N. So as long as your small n is much smaller than capital N, I'm done.
And in the thermofield double also, don't you get, how many states are there in there?
In a thermofield double state, infinite number of states.
Yeah, but so the idea, because you use the commutation relation there, the idea is that high enough energy states are being killed by the temperature?
Indeed, it's true that if I took a state, for example, that looked like AM plus 1, that had an energy, if I took an annihilation operator with energy higher than the total energy in the state, then that operator would just annihilate the state psi. So by the rules I provided before, that operator I'm not allowed to insert here. That's an operator which is like an operator of energy n squared in the CFT. It's an extremely heavy operator. Right.
Sorry, but you did make some assumption when you worked with the thermofield double and did this manipulation?
This manipulation is just kosher. This manipulation is kosher.
Are you summing over all states, all collections of integers nm there?
Yes.
So aren't you assuming that these properties of AP tilde are holding?
This calculation is a calculation in the real thermofield double where I really have two theories. I'm telling you, in a real thermofield double, you would expect this behavior.
Sure.
I've written this to mock up this behavior in the thermofield double.
I thought you were, okay.
I'm not doing this. I'm not saying that. I'm just saying that in the real thermofield double, it is indeed true that AP. So this is that I was just trying to explain the e to the minus beta fact.
Right.
The reason I put it is not arbitrary. It's put in there because this is the correct behavior that you expect for the AP tilde operators as in the thermofield double. This is now because it has this property, it is the mock thermofield double. See, AP tilde behaves the way it does in the thermofield double.
No, but now if you create the thermofield double, okay.
You can't act with states that are too high energy. That's true. That you can't act with if you just annihilate the state, you annihilate the state. Yes.
Just one clarification. So, if you have the two conformal field theories, then the picture is absolutely clear that you need both A and A twiddle and this type of pure state.
Yes.
But if you have only one conformal field theory in which the given operators are only the A's, then in some sense,
I'm trying to double the operators in a single theory.
Exactly. So A twiddles in some sense would be some functionals of the small A's.
Yes,
right?
absolutely.
Okay.
They are absolutely, they're functionals of small A's. But they're very cleverly constructed functionals that have the right properties. They commute and so on within the state. So they're functionals that are, okay, how about this property? So I got this property out. How about this property? Can I get this property out? Well, let me think of n tilde omega k on psi, which is a dagger tilde omega k into a tilde omega k on psi, okay, which is, a omega k by this rule here. This is e to the minus beta omega k. Not omega k. Sorry, and I only have p's here. I don't have any omega k's here. I can put in omega k's, of course, into AP dagger psi, okay? And then by this rule, so I should write down a rule for AP dagger also. AP dagger, the rule is the same, except this becomes an AP and this becomes an e to the plus beta omega p. E to the beta omega p, e to the minus beta omega p into AP dagger AP psi, which is equal to NP psi. Okay? So clearly NP tilde for these operators is perfectly correlated with NP. So I've achieved this relation too. Of course, on the state psi and on descendants of the state psi. Okay? So these operators are indeed functionals, but they satisfy all these properties. Okay? Okay, good. So now let me quickly mention the generalization to the CFT, and let me talk about the AMPS arguments. What's the generalization to the CMP?
Do you have an explicit construction of the A tilde in some sort?
You can do it numerically. It's a question of solving some linear equations, so we can do it numerically. Yes.
But so just to check that.
Yes, I think there's no hidden consistency condition. A hidden consistency condition is that you shouldn't be able to annihilate the state psi by acting with a finite number.
So that's the only consistency condition.
I think so. Yes, that's the only that's the only condition that tells you might get an inconsistent set of linear equations. Yeah.
Building up the thermophile double state, which is in this. I mean, how do you making the distinctions of this set Nm and Nm tilde?
Right. So the point is that a highly entangled thermal state, for all practical purposes, looks like a thermophile double state. You know, a very thermal state, a single state of a system that's perfectly thermalized, looks like a thermophile double state, as long as you don't measure very high point or very complicated correlators. A thermal state is almost indistinguishable from a thermophile double state. Okay. Okay, good. Let me just try and mention the generalization to the CFT. What's the generalization to the CFT is that everything goes through. I don't need to put in this omega p, you know, e delta p things by hand. It's automatically true that no state in the CFT is annihilated by combinations of things of this kind. If you take a finite number of single trace operators, they don't annihilate the state, a thermal state of the CFT. By the way, you can see immediately I can't do this construction in the CFT vacuum. If I have the vacuum of the CFT, then the vacuum is immediately annihilated by these O operators. Right? So I can't double the operators in the vacuum. It's very important that I'm in a thermal state which is not annihilated by an action of a finite number of single trace operators. When I say finite, I always mean small compared to n, and doesn't scale with n. Okay, so this is a construction that I can do in a thermal state, and the physical interpretation is, as Nilay said, that a thermal state is basically indistinguishable from a thermophile state. So I can't do this construction in the vacuum, and that's an important check. On the other hand, there's a question that was asked earlier, also, you know, and I don't need to impose these arbitrary incommensurate frequencies and so on, all this just happens.
I'm sorry, but you're doing more than, you know, when you say a thermal state is indistinguishable from a thermophile double state, what you mean is that the properties of a thermal state come from a density matrix, and that density matrix can also be obtained from a thermophile double state, right? No, but I'm just saying you're actually doing more, because you are saying, you know, in the same one CFT, you're constructing the analog of the partner.
Effectively, they depend on the state psi. Yeah. They don't really, you know, it's not really true as an operator that AP tilde commutes with AM, but on the state and on descendants of the state, for all practical purposes, indeed, you can find.
I mean, that's more.
Yes, it's more than that. It's more than this. I agree with that.
So you're saying Hilbert space is larger?
No, the Hilbert space is not larger. Everything is, the Hilbert space is, I was doing everything in decoupled harmonic oscillators. So Hilbert space is what it is.
So you're saying is in the, I mean, CFT is not, how can I say?
The space of operators is effectively doubled. If you look at finite, you see, the reason is that the number of operators I'm constructing here are much smaller than all the set of operators in the CFT. The set of operators here is huge. There are many operators I can write down. I'm not interested in most of those operators. See, if I start considering n, most of those operators are n point, you know, are products of n of these guys, capital N of these guys. I'm not interested in them.
So let me make sure, just a CFT which describes just outside black hole also describe inside, is that right?
Yes, that's the claim I'd like to make.
Okay.
And I'm saying that these interior operators can be constructed as, in some sense, combinations, clever functionals of some very heavy operators.
So one small clarification. So the A's and the A daggers are simple oscillator fellows. A commutator, A dagger is +1.
I can, A tilde or A's? A's, yes. I can show you for A tilde also.
A tilde also, you get +1?
Yes, you'll get +1 on the state side. Let me call this 8. You want me to show you right now? I'll show you later when I come to this.
Just a state.
I'll show you. Yes, it's true. You get 1 on the state side. I will come to it because it's related to this. Okay, let me just say a few words about the CFT. The CFT you can take, there's a eigenstate thermalization. Yeah. You just use these rules. If you take two tildes, you act with the tilde on the right first, you get an ordinary operator, then you act with the tilde on the left.
Right, means AP tilde is defined like that, but what AP tilde, is it AP again or what is it?
Oh, I don't want to talk about tilde. Actually, I'm not defining tilde as not an operation. Tilde, this is just a set of, for each operator I'm constructing a pair. There's no operation tilde which acts on an operator and takes it to another operator. I'm just defining a new set of operators.
Okay.
If you like, yeah. I don't want to talk about it in terms of, okay, let me say a few words. There's this eigenstate thermalization hypothesis for n equal to 4, which we'd like to preserve, which is a statement that in an energy eigenstate, you take a typical energy eigenstate and it has the same properties as the thermal state. So this is something that's discussed a lot, and I think we'd like to preserve it. There's no problem with that, except that if you have...
In this construction, AP tilde probably will involve more than n, I mean, of the order of n
yes.
is an AdS.
Yes.
So tilde of that doesn't make sense, because
probably not.
You don't want to...
You could define tilde to take you back, but I don't even want to think of tilde as an operator.
This definition is not going to make sense, because it is only acting on a few operators.
Yes. Yeah. So yeah.
What is, so just, can you just state a little more precisely, what is the eigenstate thermalization? Just that a typical energy state,
looks like
if you wait long enough for simple enough measurements,
looks the same as the thermal state, yes.
Why n equals 4? I would say for any interaction.
Any theory which has, which has, there's some technique, not all theories do this. So,
okay, very special theories may not, but.
And then there are some further conditions. You can write down a stronger version that holds if there's quantum chaos and so on. So there are various versions of it. I'm just saying that I'm happy to let you take an energy eigenstate. I'm certainly happy to let you take a charge eigenstate. That requires me to put a few caveats here, which is that if it's really true that my state, so let me now go to the states in the CFT, or this construction just goes over entirely. These A's I can start thinking of as O's, where O's are the modes of a single trace operator. But remember that in the CFT, I might have, if I'm saying I have an eigenstate thermalization hypothesis, I have this relation. In fact, this HCFT is like the integral of T00. Okay. But it's the integral of T00, but it's a very specific mode of T00. It's a zero mode of T00. Okay. So in this construction, when I define this rule, any operator you're allowed to insert here, you're allowed to insert any operator except for the zero modes of a conserved current, not only of T, but of any conserved current. You're not allowed to insert the J00 mode in this construction. Okay. If you insert the J00 mode, then this rule doesn't hold. I'll have to give you a modified rule, which is that the J00 in fact doesn't commute. Okay. I can tell you the commutator of J00 with AP. But I just want to, there's just a note of caution, which is that in the CFT, you really can put things in an eigenstate of the energy or an eigenstate of the charge, and then clearly this kind of, I have to modify this rule by telling you there's a non-trivial commutator between the zero mode of any conserved current. It's only the zero mode, nothing else. I need to worry about the zero mode of conserved currents. Zero mode doesn't even correspond to a propagating particle in the bulk. There's no real zero mode corresponding to the graviton, but if I do decide to insert such things, the state could be an eigenstate of them, and I'll have to modify this rule. Other than that, this construction just goes through without some of the artificial things that I put in by hand here, such as demanding that, these frequencies are incommensurate. It's automatically true in the CFT that with an action of a small number of single trace operators, I can't annihilate the state psi. And the state is not in an eigenstate of any operator I can construct out of a small number of single trace operators, except for these conserved charges. Okay, so in fact, it works much more naturally in the full CFT than it does here. Okay, let me now go to the last part, which is the resolution of all the AMPS arguments. Yes. Yes. So 10 minutes, I can resolve all the AMPS arguments, but we started at 1:15, no? Yeah. No, I think we're done. Okay. Okay, so let's actually once you grant this, you see the controversial thing in this is granting the existence of these operators. I want to point out that obviously this construction is not accepted by everybody. If you ask M and P, they'll tell you we don't want operators like this. Okay, we don't like operators that are defined in the state. So there is an objection to this, which we'll discuss. If you grant me operators like this, and I just want to point out everything goes away. Okay, how does strong subadditivity go away? Now let me take a particular mode NP. Okay, so I have some number of frequencies. Remember they're omega 1 to omega n. Let me consider the system corresponding to a particular mode. Okay, let me call this the system B. This is what Sandeep yesterday was calling in this particular state, because things are entangled. Okay, so I hope it's clear. If you take more than half the number of frequencies, it's entangled with this particular frequency that I picked out. This is what I'm calling my system B. So let me remind you, the AMPS paradox went by saying there was a black hole, there was a system B, there was a bit being emitted B, there was a partner bit which I call C, or B twiddle yesterday, and there is the early radiation which you call E. So let me call this E. No, I'll call it E. It's no problem. Okay, SEB is smaller than SE. Okay, so this is E. This is the old radiation. Now I have to set this up in this model. So this old radiation is, say, all the frequencies above some amount, all the frequencies that were emitted early on. So SEB is smaller than SE, because as long as E is larger than half the Hilbert space. So if I go to, that's like saying you're after the page time, SEB is smaller than SE. Also, it's true that clearly, if you look at the, NP is, you're not in an eigenstate of NP. Okay? So you can compute the reduced density matrix for NP for this system B, and SB is not equal to 0.
So E is the collection of what? All
of some number of frequencies, some frequencies. So say 3n, you pick your 3n by 4 frequencies. There are n frequencies in this game. You pick 3n by 4 of them.
What I mean is for each frequency you can have arbitrarily large number of photons, right?
So I'll take the Hilbert space that corresponds to them. Yeah, you can have arbitrarily large number of photons.
So that is E.
That's E.
And
That's my setup.
P are some oscillators not in this set.
B is some particular frequency I picked. I pick a frequency.
And not in the set.
Not in this set. Not in this
Okay,
set.
just one particular frequency.
That's right. So SEB is smaller than SE because these frequencies are entangled with this guy.
So just even on general, without page time, anything that would be true.
Yes, there's no page. This 3n by 4 is what is meant to mock up the page time. If the number of frequency in this set are smaller than n by 2, it's not clear that this is true. SEB, E may not be positively entangled with E union B may not have a smaller entropy than E.
Okay.
This is the statement that the number of you're mapping more than half the Hilbert.
Okay.
SB is not equal to 0 because effectively it looks like you have some thermal state here. But I just told you that I had these other operators that I called NB twiddle that satisfy these properties that were perfectly correlated with this guy. That's my analog of my system B twiddle. So what's happening? What's happening is that typically if you look at these NB twiddle operators, they act on this set. Okay, so this is a precise realization of this idea of black hole complementarity that we've been discussing. The interior operators, the operators that you think of inside, these NP twiddle, AP and AP twiddle dagger. The set of operators which you want to be dual to this, which you want to form the set B twiddle. Okay, this is my set B twiddle. This acts on E. It's not independent of E. In fact, I can show you that it has to act on E. It has to act on E. So in fact, this is not forming some independent sector of the Hilbert space. However, it's constructed so that the commutators of this guy with any guy in this set are 0, as I showed you here. Or the commutators with any set of 10 of these guys or 100 of these guys are still 0. Okay? So the strong subadditivity is resolved by complementarity, but there is a counter argument to that, which is, if you do that, you typically tend to get large commutators, and it's true. This is a very specially constructed set of operators which is designed to get the commutator 0, okay, as we showed. So this is done. Okay, so this is resolved by complementarity, or what's called RA equal to B. Yes.
Just to understand that,
yes.
Your strong subadditivity,
let me phrase strong subadditivity in the following way.
Okay, go ahead, please.
Given an operator, NP, if you like, I can do this for spin operators, for a spin chain where it might be clear. Given an operator NP, it looks like there are two operators in the Hilbert space that look like they commute, and which are perfectly correlated. You see, given an operator N and a Hilbert space, you can always find some operator that happens to, be entangled with this, that happens to be perfectly correlated. This is from what you said yesterday, that the entropy tends to go down. So if I give you an operator, I can always predict the result of that measurement by measuring the other half of the Hilbert space. That's something that's just true on general information theoretic grounds. The question is, how are you finding another operator that also predicts the result, and that tends to commute with the old operator? So here, it looks like I have another operator that tends to commute with any operator I construct out of here, that looks like it commutes, but which also predicts the result of NP. And the reason this is happening is because it doesn't really commute with NP.
With all of E.
As an operator, it doesn't commute. But within a state, within any correlation function, it commutes. So, it's cleverly designed so as to commute to a very great extent. You can't detect the lack of commutativity unless you measure an endpoint correlation function. Okay? Okay, and now how about this lack of a left inverse argument? Let me remind you what the lack of a left inverse argument was. The lack of the left inverse argument went as follows.
No, but
the infalling observer's paradox is resolved by...
So the infalling observer can measure some operators here, some A omega operators. He can measure this P twiddle operator.
Yeah.
It's true that these operators in some sense carry the same information.
Yeah.
Because these operators do act on E. But he can't measure the lack of commutativity of these operators. Now the interior operators, these are the operators that the observer measures inside, in fact act on the early radiation, act on the frequencies that were emitted before. So, these operators act on this set. But you can't measure the commutator within a correlator unless you take an endpoint correlator. As
so the infalling observer has to first perform measurement on all the...
Has to perform an endpoint measurement.
Yeah, so all the radiation which has been emitted?
Yes.
and then fall in.
Yes, but more importantly, he has to perform a capital N point measurement. Measurement with correlation function with scales like capital N, otherwise he can't detect the lack of commutativity.
Okay. So it's not a one-by-one measurement.
It's not a one-by-one measurement, or it's not like he can take the sum of n different measurements. He has to really measure an N point correlated thing. And if you do that, then I think I'm not going to say semi-classical space-time holds in any sense, if you measure an N point correlated.
So that is resolved.
That's the resolution. The counter argument to this is that, the commutator looks like it's large in any such model you build up, and indeed this is true. We struggled with this for some time, but these operators seem to resolve that. Okay. Now what about the lack of a left inverse argument? Lack of a left inverse argument goes as follows. Think of this this same model. As Penta asked, what about the commutation relation of the AP tildes with AP? What if I think of this commutator, where both of these are tildes? You can check just using these rules. This is AP tilde into e to the minus beta omega into AP dagger on psi. So let me first consider this product. Okay, and now I use, so this is by rule 1. I'm just considering the product of AP tilde dagger and AP. That's this. But now by the second rule, I move it through and I get a factor of e to the plus beta. So this is the same as AP dagger into AP on psi. Conversely, if I take AP tilde into AP tilde dagger, I get the other result. Okay? So indeed, it's true that AP tilde into AP, sorry, I wrote it the wrong way around. Never mind. AP tilde into AP tilde dagger psi on any operator, as long as the operator doesn't contain n insertions, is indeed equal to A psi. So this operator for all effects and purposes behaves like it's 1. It's not really 1. And this operator is something that has some complicated matrix elements that you can't detect unless you measure an endpoint correlation function. Good. So this looks like it's 1. Now the AMPS question is, how can this be? Because you can easily check that this operator, AP dagger, that I'm calling AP dagger, in fact tends to reduce the energy. A tilde P dagger tends to reduce. Like AP. See, AP acts like A tilde P acts like AP dagger, and A tilde P dagger acts like AP. So it tends to reduce the energy. But if you really, and so the contradiction we tried to set up yesterday was, that how do you have this relation? Dagger minus A tilde P dagger A tilde P is equal to 1. Okay, if this is true, then this operator AP dagger has the left inverse. The left inverse is given by into AP dagger is equal to 1. But it can't have a left inverse because AP tilde dagger maps states of higher energy to states of lower energy. So how does it have a left inverse? Because there are fewer states at lower energy than there are at higher energy. That's true of this decoupled harmonic oscillator gas also. So how is this happening? It's happening because this is not obeyed as an operator relation. This is obeyed, in fact, within states. So if you really look at the global structure of this operator psi, it maps things within this interval that I talked about, m minus delta to m plus delta. It maps some subset of states here to some subset of states in m minus p. Some subset of states at the energy p to some subset of states in the energy m minus p. In fact, I can choose this AP tilde dagger operator to be rather sparse. So this is it can have null vectors while seeming to obey this relation within any finite point correlation function. Okay, so that's how the lack of a left inverse argument is resolved very naturally by this explicit construction. Okay, what about the NA not equal to 0 argument? That's the last argument of Marolf and Polchinski. How do you resolve that? We resolve that. Let me just remind you what NA is. NA is in fact very simply related to this. This NA is given by NA, let me call it for the mode P. So let me remind you of the NA not equal to 0 argument. It was the argument that for a typical NB eigenstate, an eigenstate of one of these A's, it would look like the occupation number for the infalling observer, the modes for that would be non-zero. But what are the modes for the infalling observer? In fact, you can construct them. You know what the Bogoliubov transform is. You can buy alpha P dagger alpha P, but this alpha P is just this guy that I wrote here. It's AP twiddle minus e to the minus beta omega by 2 AP dagger. Okay, or it depends on which. There's one more operator which goes the other way. Okay, depends on what kind of convention you choose. Okay, but in fact, it's just this Bogoliubov transform. And indeed, this alpha P goes and annihilates the state. So in fact, with the operators constructed in this fashion, in this clever fashion, In fact, it's true that NA on psi is 0. You give me a state, I construct an operator NA and I find it 0. Now, what went wrong with the Polchinski-Marolf argument? What went wrong is that this operator depends on the state. And the whole argument of doing a trace and then making a change of basis doesn't work because this operator, in the Polchinski-Marolf argument, which I can review in detail if you like, they were trying to compute this trace of NA over the microcanonical ensemble. But the trace of NA is, if this NA is a state-dependent operator, this NA changes as you go down the trace. And so it's not the same operator you're looking at. And in fact, if you try and change basis to a basis of this NP, this NB eigenbasis, in that this construction doesn't even work because those are the firewall states. In fact, those are exactly the firewall states, the states which are eigenstates of these ordinary operators. Okay? So in any case, I just want to say that in this construction, you can explicitly construct the modes for the infalling observer. These are the modes. You know the Bogoliubov transform. You check NA and it's 0. So the Polchinski-Marolf argument doesn't hold. Okay, so I think that resolves the AMPS arguments. Let me just make a few comments and then I'll end. So I want to say a few things. There's of course so I think that the summary of the AMPS arguments, all these arguments, is really that you need to interpret these operators in this sense. Okay, the operators that you get in quantum gravity are state-dependent operators, and as I try to show you, you can very explicitly get rid of all the arguments if you assume this. Now this is not, just before I go to the physical interpretation of this, I'll come to that in a minute, which is an important question. I want to mention that this whole construction we are doing actually has great similarities with something called the Tomita-Takesaki theory, which is some theory in the development of von Neumann algebras. I don't have time to review the link right now, but there's this Tomita-Takesaki theory, which in fact does precisely this. It starts with some algebra and tries some algebra of operators and gives you a prescription to construct the commutant of the algebra, which is what we are constructing here. So I can try and review in some more detail, but in fact there is some discussion within the mathematical literature that we are not yet completely familiar with, Kyriakos and I at least not completely familiar with, of the state dependence of this. So in fact there's something called the Korn's cocycle, which talks about the state dependence of the commutant of a von Neumann operator algebra that you get by using this Tomita-Takesaki construction. If you like in the discussion, I can try and tell you in more detail what this Tomita-Takesaki construction is. It's actually a very simple construction. It starts with some universal kind of antilinear map that you can define on a von Neumann algebra, and then constructs these, really the analog of these tilde operators from what's called a polar decomposition of this antilinear map. So if you like, I'll be very happy to tell you more, but since I promised to end soon, let me say a few words about physical interpretation and then I'll end. Okay. So I just want to point out though that there is a link between this construction and something that's well known in the mathematical quantum field theory literature, which is this Tomita-Takesaki theory, which I don't have time to review here. Let me just say a few words about the state dependence of this. As you can see, as I hope I've persuaded you, that really the AMPS arguments in some sense to me seem to be arguments for state dependence. The alternative, and this fact that there is state dependence is, I think, already visible outside the black hole horizon. Remember at the beginning of this talk, I wrote down some formulas for what I call the local field in the bulk in the thermal state and what I call the local field in the bulk in the vacuum. And those formulas were different. The mapping between CFT operators to local bulk operators depended on whether I was in the thermal state or whether I was in the vacuum state. So in some sense, you already see a sign of state dependence at this level. On the other hand, what Polchinski and Marolf would like to argue, as we discussed yesterday, is that you can write down some very complicated linear operator, very complicated operator which is state independent, that reduces to the correct limits on, when you insert in the thermal state and when you insert it on some other state. Okay? And there are many questions about such a construction. For example, you could say if you could write down such a local bulk operator independently of specifying the state, how do you even specify the coordinates of this? There was some discussion about coordinates. The coordinates of the black hole, the geometry of the black hole is very different from the geometry of AdS. So how do you specify the coordinates in some state independent way? Before I can even start to talk about coordinates, I need to talk about what state the theory is in. Okay? And the answer is, well, maybe you have some state independent definition of coordinates. You start from the boundary, you jump in for 10 seconds of proper time, you turn towards the direction of highest curvature, you go a little bit there, you fall some more, free fall some more, do something like that, and you end up at a point. This is some prescription for giving you a point in any kind of state, and then you write down some local operator in this kind of state, which is state independent. So it's not clear to me that something like this can be done. It clearly hasn't been done in any explicit fashion. And we already see, even outside the horizon where a lot of this construction is very uncontroversial, that it looks like at least this state dependence doesn't commute with the 1 over n expansion. If you look at the leading term in 1 by n, that already looks state dependent, but maybe there's some way of writing down an infinite series in 1 over n that automatically resums itself. So anyway, my summary of this whole thing is that I think that a lot of the AMPS arguments are about this, whether you can independently of the state and independently of the background localize operators in quantum field theory and talk about local operators. If you cannot, and if you're willing to allow me to say that I can talk about operators in quantum gravity only about a given background and small excitations about that background. So these are effective field theory operators. You give me a background, some space-time emerges because I'm in that background, then I make some excitations about that space-time, and I can talk about operators that act in this small Hilbert space, not that take you from one state in the theory to some other state very far away. If you're willing to grant me this, then indeed I think the AMPS arguments don't hold, because the tacit assumption is that that all these operators are state independent. But on the other hand, if you're going to insist on state dependence, I think I'm persuaded by these AMPS arguments, and you're led either to the firewall or to the conclusion that the interior of the black hole doesn't exist. Okay, so I'll stop there. We can go on for 2 minutes. Still one. Okay. Yes, sir. Okay. Yes. Fine. Okay.
So we will.
There is a discussion.
Yes. Sure. Yes. Sure. Okay. Yes.
So these tilde operators you're defining for a finite number of such insertions and so on, right? So what breaks down physically if that's not the case?
If you insert too many such insertions, you see my linear equations, this becomes an overdetermined set.
So technically it's clear, but
what breaks down physically is the statement that if you start looking at n-point correlators, then you can't talk about a semi-classical space-time in that approximation. If I start looking at, if I make n-squared insertions of the stress of a graviton, in what sense am I talking about the original black hole geometry?
You're changing the thing.
You're changing the thing in a very violent way. So n-point correlators should not have a good semi-classical interpretation. These n-point correlators also in the 1 over n expansion down by 1 by n to the n in some sense, as we discussed last time. They're extremely suppressed quantities. They're very small quantities. So why should some semi-classical picture of the bulk make sense for an n-point correlation function? You could ask the same thing for the gas in this room. You have some smooth density profile, you can measure the density, you can measure correlations of the density between one point and the other. Now you can ask, let me measure an n-point correlator where n is the number of atoms of the gas. That description doesn't have any answer in terms of a smooth density profile. So, I think it's natural to say that n-point correlators don't have a natural interpretation in terms of semi-classical.
Okay, I think we will close this session here now, and let's all go down into that grass in front of the gate for a photograph. Just be careful, there's a resident layer of cobras there. And we will come back at 2:15.